So today we will continue on with more hypothesis tests, and these are just more methods that that we can use. So really, so far, all we've covered were the t-test and the paired t-test, which is pretty much the same thing, except now you've got paired data. Okay, so t-test is used for what we call a numeric response. But distinguished by a categorical variable, so we have two groups. Okay. Numeric response, categorical variable, and this is and then we have the t-test for independent groups. And then we have a t-test for paired data. All right, just to on the first few quizzes that I graded, I didn't take off any points, but just so you know, the hypotheses for independent groups, it's always, you got to use mu, not y bar or x bar or anything like that. It's going to be mu1 equal to mu2, or mu1 minus mu2 equals 0, or something like that. Okay, so that's for independent groups. And then for paired data, the null hypothesis is that d, the actual difference, equals 0. Okay, so there's no, it's not mu1 or mu2 for paired data. It's that the difference is equal to 0. Okay, I didn't take off any points for that if you didn't write down your hypotheses, but this is there's an important distinction there. Or if not d, also acceptable would be mu sub d is equal to 0. That's also acceptable. Okay. The mean difference is equal to 0. Okay. So mu sub d or d, that's fine. Okay. There were a few assumptions that had to be met, or some conditions that had to be met in order for us to use the t-test. And that was, we're under the assumption that the sampling distribution looks like the normal distribution. Okay. So in order for us to use the t-test, we assume that the sampling distribution looks like the normal. And in order for that to be the case, either our samples have to be large. Okay, well, of course, when we select our samples, they are selected randomly or independent of one another. And our samples either have to be large, or the population has to be normal. Okay, so we have a few conditions. So conditions, our samples are random / independent. Basically, our sample is not too big. The one that usually, well, maybe the samples are not random independent is probably the one that's most commonly violated. But another one that's frequently violated is the sample needs to be large enough. And we said if the population is normal, any sample is large enough. But if the population is not normal, then you need a larger sample. And the rule of thumb was samples of size 30 or more, generally large enough. Rule of thumb. Okay, so this should be reviewed, right? So what happens if these conditions aren't met? Okay. So in particular, if our sample is not large enough, meaning our population is not normal and we don't have a large sample, what do we do? Okay. Can we still do a hypothesis test? So the answer is we can do a hypothesis test, but we can't use the normal distribution or the t-distribution as our basis for basically as our basis for the probability and statistics part. Okay, because we ask what's the probability of observing a sample like this or something more extreme if the null hypothesis were true. What's the probability of getting our data if the null hypothesis were true? So now, and we would answer that using our knowledge of the normal distribution or t-distribution. But now, because these conditions aren't met, we can't use the normal distribution or t-distribution to answer these questions. Okay? And so this opens up as kind of our introduction to this whole other range of statistics or field of statistics known as non-parametric statistics. And these calculate probabilities and statistics, but they are not based on nice functions like the normal distribution or things like that. They make no assumptions about the data. Okay? What's a distribution of where the data came from? And yeah, that you can take entire courses on non-parametric statistics. We're really only going to spend maybe 30 minutes on it in this class, okay? And you're just going to learn one non-parametric test, okay? And it's one of the kind of our most basic non-parametric tests. But yeah, there's a whole range of them. The book covers a few more in the paired data section. There's a bunch of non-parametric tests for paired data, but we're just going to skip those. Okay, so the non-parametric test that we're going to learn is known as the Wilcoxon-Mann-Whitney test. And it is, if you take an, okay, so our book teaches the Wilcoxon-Mann-Whitney test, so that's what we're going to learn, okay? If you take another statistics class, you are more likely to learn something called the Wilcoxon rank sum test, okay? It turns out that the Wilcoxon rank sum test and the Wilcoxon-Mann-Whitney test are exactly the same, okay? In terms of their, in terms of what they're doing, okay? The math turns out to be exactly the same. But the process looks and feels very different, and so that's why these two tests existed, because one group came up with the Wilcoxon-Mann-Whitney test, they came up with this thing, and then I guess Wilcoxon later on, or whatever, developed the Wilcoxon rank sum test, and they looked very different, and they felt very different, but it turned out that they were exactly the same. But can also be the Wilcoxon rank sum test. And the process for the Wilcoxon rank sum test is different, and you use a different set of tables and things like that. But whatever. Okay. Wilcoxon-Mann-Whitney test. This is what we can use. This is a test we can use to compare the I guess the distribution of two samples, or to compare two samples and see if their or populations, respective populations, are the same or not. Okay, so with the t-test, the null hypothesis was that the mean of population 1 is the same as the mean of population 2. Okay, and basically you were making a test on a parameter of the population, which was the mean. But with the non-parametric test, we don't have a parameter anymore, so we can't say the mean of population 1 is the same as the mean of population 2. So we get this weird, oddly worded phrasing, and so our null hypothesis, so we're going to observe two samples, and the null hypothesis basically says that the population that produced sample 1 has the same distribution as the population that produced sample 2. And we can't use any kind of symbols to shorten this up, okay? And then the alternative would be that one of the populations tends to produce either produce larger or smaller values than the other. Okay. So this would be a non-directional alternative. If we wanted a directional alternative, we would have to say the population that produced sample 1 tends to produce larger values than the population that produced sample 2, or something. We have to specify which one we suspect produces larger values than the other. Okay. So this will be non-directional. And then the directional alternative specifies which population in general, non-parametric tests are less powerful than parametric ones. Okay, so what does that mean to be less powerful? So I'll write this down and you can think about it.
Has a higher probability of committing a type 2 error.
Okay, has a higher probability of committing a type 2 error, meaning
Larger beta.
okay, so what this means is that so the null hypothesis says basically that the two populations are the same, have the same distribution, or if it was a parametric test, so if we were doing a t-test, we're saying that the two populations have the same mean. Okay, so if that notion were false, if the two populations actually had different means, or the two populations did not have the same distribution, okay, the non-parametric test is less likely to detect that difference than a parametric test. Okay, so a t-test, if two populations have a different mean, and if you've collected enough data, the t-test is more likely to say, to get you to reject the null hypothesis than a non-parametric test. Okay, and that makes sense because the t-test puts assumptions on the population. Okay, we're assuming that the sampling distribution follows a normal model or something like that. Okay, with the non-parametric test, we're throwing out a lot of these assumptions. Okay, so because we can assume we're assuming a lot less, we're more willing to, I guess, give a little bit more benefit of the doubt to the null hypothesis, if that makes sense. Okay. So anyway, that's something to keep in mind. But sometimes it would just be flat out wrong to use a parametric test because the assumptions or conditions are not met. Okay. All right, so let's talk about how to do the Wilcoxon-Mann-Whitney test. Okay, so. All right, so let's say so I'm just going to use the data that this that the book puts here. So we go to the forest and somehow we are going to measure soil respiration. I don't even know what that means, but apparently you look at some sample of soil and you see how much carbon dioxide it either gives off or gives off by a soil pore. Okay, so somehow we can do this, and we go to two different regions in the forest. Okay, so one is where there's a lot of things growing, and then another region is where it's a little bit more barren. And we want to know, is the soil respiration different between the two groups? Okay, so this is the growth area. That's much space there. So the growth area, the numbers that we observe are 17, 20, and I'm going to put these in order from smallest to largest. 64, 190, 315. So these are the soil respiration data. Okay, and then in the area where there was a gap in the growth, the numbers were 6. So when you come across data, all right, maybe your initial reaction would be, okay, I've got two groups here, let's do a t-test, okay? And that would probably be what I would initially think of doing at first. But then when you take a closer look at the numbers here, okay, this seems like it could reasonably be normally distributed, okay? There's nothing too crazy going on here, okay? But over here, the numbers that we've got going on here, we've got numbers like 315, 190, 170, and also numbers like 70, 20, 22, 64. So we got, it seems like we've got some numbers in kind of this, in like the same region as we have over here, and then we've got some very extreme data points here. So it seems like we've got some very large outlier type outliers in the growth data. So this would be a good candidate to use for the Wilcoxon-Mann-Whitney test. Okay, so because of this, probably our conditions to use the t-test are not met. Okay. So, we should use non-parametric. Wilcoxon-Mann-Whitney test. Okay, so this is how we go about doing this. We just so first you have to arrange all of your numbers in order from smallest to largest in the two columns. And then you look at this data point, and you say how many in the other table, or in the other column, are smaller than this data point. So my first number is 17, and then I count how many numbers over here are smaller than 17. So I got this number 1, 2, 3, 4. I've got 5 numbers that are smaller than 17 in the gap column. So I put 5 there. Okay. And then I go to 20, and I do the same thing. How many numbers are smaller? 1, 2, 3, 4, 5, 6. Okay, and then with 22, I do the same. 1, 2, 3, 4, 5, 6. Anytime you see a tie, the ties count as half. So this would be 6.5. Okay. If there was another 22 in here, each of those 22s would count as a half, and I would put a 7 here. Does that make sense? Okay. And then I do that. So with the 64, I've got 1, 2, 3, 4, 5, 6, 7, 8. All 8 numbers are smaller. And at this point, all I'm recording are 8s. And I do the same over here. I'll count how many are smaller in the other column. 2.5. How many then you add these up. Okay, so the sum of this column is 6.5, and then when you add all of these numbers up, you get 49.5. And then we just take the larger number, and this becomes our test statistic. Larger sum. And, the symbol they use for this is a U. I'm not sure why, but use of S. U. Okay, so this becomes our test statistic. And then we go to a table with a bunch of value points for the Wilcoxon Mann-Whitney test. And the way we look it up is the group with more data points. This is going to be N, so the group with more data points gives us our N. So we've got 1, 2, 3, 4, 5, 6, 7, 8 in that one, and 7 in this one. So our N is 8, and our N prime, and then the other group is our N prime, and so we have 8 and 7 as our N1. I'm sorry, is it N1 and N2, or is it N and N prime? I forget.
N and N prime.
N and N prime, good. So everything has different notation. Okay. So now we go to our Wilcoxon Mann-Whitney table, okay, and then we look up N and N prime, okay, and then so somewhere down the column, okay, there will be N is equal to 8, and there it goes, I think, it starts at 2, okay, and it goes 2, 3, 4, 5, 6, 7. So we go to this row where N is equal to 8 and N prime is equal to 7. And the numbers that we have there are 40, 43, 46, 48, and 50. Am I counting this right? Okay, so our number 49.5 falls in between 48 and 50. Okay. So my p-value is going to be in between. I don't know exactly what it is, but it's 49.5 is in between 50 and 48. So my p-value is going to be between 0.021 and 0.0093. Does that work? The using of the Wilcoxon Mann-Whitney table. Okay, and these are generated by the theoretic distribution of just rearranging in this case 15 numbers, and seeing what if we could do this every possible arrangement of 15 numbers into two columns of 8 and 7, and counting out all the different rankings. Okay, so it's a little bizarre how they generate these, but this is what we get. Okay, all of the values, and to help you keep track of this, all of these values here, they are for non-directional tests. Okay, so I know the t-test, the tail probability is for a directional test, and for a non-directional, you have to double it. These ones, they are for a non-directional test, and if your hypothesis test is for a directional test, you have to take it and divide it in half. So, I know it's like awful, but it's written at the top of the table to help you keep track. Okay, it'll say the corresponding p-values for a non-directional alternative is in italics. Directional p-values are found by dividing the numbers in italics in half. Okay, so it's written right there. There you have it. Okay, and so this is it for non-parametric tests that we will cover in this class. Okay, and again, it opens up the whole. There's a lot of stuff. Okay, and it was a pretty popular field of research for a while. And so yeah, I know in chapter 8 we only covered basically 8.2, which was on the paired t-test. The rest of chapter 8 is all on just more non-parametric versions for paired data. Okay. Which may or may not be necessary for things that come across. So, okay, is that all right? And so that will conclude our portion for chapter 7, that last bit in chapter 7, and then and so now we're going to move on to something entirely different, which is chapter 9 and 10. So it feels like we're covering quite a bit today, but it's not too bad. Chapters 9 and 10. And this is all on now categorical data. Okay. So chapter the t-test we use to compare numeric data between two groups. With chapters 9 and 10, now our response is categorical data. So before we could say, are the means of two groups, is the mean IQ of students who go to this college, is it equal to the mean IQ of students who go to another college, or something like that. Now, our response is categorical data. So we could say, is the proportion of men in the Army equal to the proportion of men in the Navy, or something like that. Okay, maybe not, probably not. Do they allow? Women are not allowed into submarines, right?
You're allowed in. I just don't think you're allowed to be on one.
Or they don't enlist women into submarines or something like that, right? Well, I don't know. Yeah, I guess you can walk onto one, but
they announce over the loudspeakers when women are on submarines. I was on one with my friends in the Navy, and they were like, "To everybody, there's a girl in the boat."
That's exciting. Yeah. Or embarrassing. Okay, but anyway, so now our response is categorical data. So things like gender, men and women, or political attitudes, or something, this group or ethnicity, or if we're talking about vehicles, you know, whatever, you know, make and model or things like that. Just categorical, we're dealing with categorical data. So in chapter 9, we are introduced to something called the chi-squared test. Chi-squared goodness of fit test. Okay. So basically, all of these categorical. Sorry, my brain is all messed up right now. Okay. When we're doing hypothesis tests for categorical data, we're almost always going to use the chi-squared test. Okay, so it's not a t-test. Now we've come across something else called the chi-squared test, and that's derived by somehow squaring the normal distribution and adding a bunch of identical things, but it doesn't matter. Okay, so the chi-squared test. The first one is known as the chi-squared goodness of fit test. Chi-squared goodness of fit test. Chi-squared goodness of fit test. And what this is you've got in your brain, you think the population has certain proportions. Okay, so maybe in my brain I think the United States is 50% male and 50% female. Okay, or I'm thinking if I roll a die, a fair die, I should see the number 1 show up as equally often as the number 2, as the number 3. Like each face should show up 1/6 of the time. Okay. So in my mind, the population has certain proportions for each category. So maybe the USA, probability, male, and probability of female, 25, or for fair die, probability of 1 equals 6, which equals probability of 2, so on and so forth. Okay, and they don't have to be equal probabilities here. Okay, it doesn't have to be 1/6, 1/6, 1/6. You could also just say, okay, I think in the Army, I believe probability of male is this, and probability of female is something else. I don't know. How much of the Army is male? 85%? I have no idea. Maybe it's lower than that. Okay, so anyway, I just have some numbers in my mind of how much each proportion for each category is. What the goodness of fit test does is you go out and you collect data, and you want to see if that data fits the proportions that you had in mind. Collect data from a random sample. Okay, so let's say somebody tells me that they believe the Army is 85% male and the 15% female. Okay, and I say, okay, well let's go see about that. All right, And somehow we obtain a random sample of people in the military. Okay. And this is our random sample. So let's say 100 people. And I count them up, and somehow, so when I count them up, I get, let's say I get 89 males and 11 females. So this is what my data shows. And so the question is, does my model, does it fit the data? Or is there a discrepancy between the model and the data that tells me my model is bad? Okay, what do you guys think? If somebody says 85% male and 15% female, and then you take a random sample of 100 people in the Army and you get 89 males and 11 females, do you think this is good or bad? It's okay, maybe not okay. Okay, well, this is where we do the chi-square test. Okay, so this is why it's a goodness of fit test. It's how good or how well does the model fit the data. Okay. Goodness of fit test. How well or good does the model fit the data? Alright, so according to our model, if I sampled 100 people, how many males would I expect to get? 85, okay? So, according to the model, we have expected numbers. We expect 100 times 0.85, 85 males. And it's okay if you get a decimal here. Okay? If the model says you expect 85.3 males, that's fine. Okay? It's okay to have decimals. And we would expect 15 females. So we calculate a chi-squared statistic by taking the difference between what we observed and what we expected. And then we square it and divide by the expected. Okay. So anyway, our chi-squared statistic is for each category, we take what we observed, and we subtract what we expected, and we square that difference, and we divide by what we expected. And we add this up for each category that we have. So in this case, what I observed was 89 males. I expected 85 males. So I'm going to square that difference and divide by 85. And then for the females, I expected, or I had 11 females, but I expected 15. get 1.255. Add those two numbers together. Okay, so my chi-squared statistic is 1.255. Alright, and then so in a moment we're going to go to our table and figure out a p-value from it. Okay? But before we do that, let's just think, what was my null hypothesis? Yeah.
That there would be no difference in what we expected in the model and what we found.
Yeah, so the null hypothesis basically says the proportions in my model are correct. Namely, that the proportion of male is 0.85 and proportion female is 0.15. And then the alternative is my proportions are not correct. And so as it's stated here, it's a non-directional alternative. Okay, we'll talk about what it means to have a directional alternative. The proportions are not correct. At this point, it's not correct. Alright, so our chi-squared statistic is 1.255, and this is somehow a measure of the discrepancy between our data and the model. When we go to our chi-squared table, we're going to notice there's a column for degrees of freedom. Okay? And so for a goodness of fit test, the degrees of freedom is equal to the number of categories minus 1. Okay. So in this case, I've got 1 degree of freedom. And we can kind of understand that because if I tell you I selected 100 people total, and I tell you that 89 of them were men, instantly you know that 11 had to be women. Okay? So once you can change one number, but the other number is kind of fixed once that number is specified. Okay? And if we had 3 categories, once you select 2 numbers, that 3rd category is going to be fixed so that it adds up to the total number. So that's why degrees of freedom is number of categories minus 1. Alright, so what do? We go to our table, chi-square table. We go to the row 1 degree of freedom, and we're going to look for where 1.255 fits. So this is table 9. I've got 1.64, 2.71. Okay, so 1.255 fits right there. So my p-value, I don't know exactly what it is, but I do know my p-value is going to be greater than 20%. So this, so from this we would say we do not have evidence that proportions in our model are not correct. And that means anytime I select 100 people, if the true proportion in the population were 85% male and 15% female, if I selected 100 people, then over 20% of the time, I would get a sample where my chi-squared statistic ends up being 1.255 or something larger than that. Okay. Is that feeling okay? All right. We can also have directional tests for chi-squared tests, okay? But directional tests are only allowed when you have only two categories, okay? Only when you have two categories. So again, let's revisit this problem here. So in this case, our null hypothesis is that the proportion of male is equal to 0.85, and the proportion female has to be 0.15. A directional alternative. So somebody says, I think the Army is 85% male and 15% female. Okay? And someone says, no, that can't be right. There's got to be more women than that. Okay, someone says there's got to be more women than that. So that would create a directional alternative. And specifically, it would be that the probability of female is greater than 0.15. Okay. And because there's only two categories, it forces this to then be less than 0.85, right? And because there's only two categories, we could even actually ignore this and just look at proportion female is 15% and proportion female being greater than 15%. And we can ignore this because we know proportion not female would then have to be whatever else. Okay. So and it only works for two categories. So let's say if we were not talking about male and female, but we had something where there were more than two categories. So let's say we were saying, and the proportion of maybe we were talking about different races in the military. Maybe we could say proportion white is 50% and proportion black is 30% and proportion just for now let's just do other and do 20%. Okay, so if this was the null hypothesis, the alternative hypothesis states that at least one of these is wrong. Okay? Now if somebody says, oh, that can't be right, it's got to be I think the military is more than 50% white, okay, and they put this, then where does, what happens to the other two categories, okay? It could be that we don't know how to modify these with respect to should it be less than or equal to or something, okay? Does that make sense? So if I change one category, I don't know what happens to the other categories. So if you've got more than two categories, you cannot do a you cannot have a directional test. So directional test only for only when there's two categories. If you wanted to test that, you can do white versus non-white, and then you'd have only two categories. But if you've got more than two categories, you can't have a directional test. Okay, so let's say so this is our thing, and we went out and we collected data, and let's say our data shows 89 males and 11 females. Alright, so then what happens at this point? What happens when we check directionality? So someone says, I think the proportion of males is 85%, proportion of females 15% of the army. And someone says, no, that can't be right. There's got to be more females than that. And they say, okay, well, let's go take a random sample. And they take a random sample of 100 people, and they get 89 males and 11 females. So at this point, we don't even have to go on with the test. We can just say, we collected data, and our data definitely does not support the alternative. Okay, we have no evidence supporting the alternative. So if this is our data, we'd say we have no evidence to support the alternative or reject the null. On the other hand, if we went out and collected data and we got 80 males and 20 females, then yes, now we possibly have data to support the alternative. Okay, so this lines up with the directionality of our alternative, and then now we have to go through the test, and we do our chi-squared statistic is equal to sum of observed minus expected quantity squared over expected. Okay, so our data shows 80 males and 20 females. What we expect from the model is 85 males and 15 females. Okay, so now we go through the test. 80 minus 85 squared over 85 plus 20 minus 15 squared over 15, and I get some number. Alright? Okay, so now I go to the chi-squared table. Looking up. I still have, so my chi-squared statistic is 1.96. So that fits in between here and here. So my p-value is going to, these are the tail probabilities, and so again, if you read the chi-squared table up at the top, it says the column headings are for non-directional p-values, and if it is directional, the p-values are found by dividing the column headings in half. Okay. So here are p-values. Our p-value, the tail is in between 10 and 20%, so our p-value is going to be in between 10% and 5%. And so we have to decide an alpha to determine what it might be. Okay. Our alternative here was that. Alpha were 5%, we would not reject. Okay. I hope this makes sense so far. All right, let's take a little break. We'll come back at like 8:45.